Hi everyone, welcome to Introduction to Logic. So this is going to be your section 1.1 and 1.2 of Zybook. We're going to go through different types of propositional logic and what it means and such. So propositional logic can also be related to propositional calculus. It can also be related to sentential logic. Essentially, again, the objects are called propositions, and proposition is a statement that can be either true or false. There is no way that it can be both, but it's a simple factual statement which is either true or false. You have different small letters such as P, Q, R, S that denote these propositions, and then you have different conjunctions and different symbols that help understand how those statements tie in together. Now, again, a proposition is called a truth value, or the value of the proposition is called a truth value. This is denoted by T or 1 if it's true, F or 0 if it's false. Essentially, it's as simple as that. Whether you do math or whether you do something else, those are going to be your values. When you tie it into other things, your opinions, for example, your interrogative statements, imperative statements, these do not become propositions and are not propositions. Your truth table is drawn out something like that, where you have your proposition and then you have a value of that statement. So 0 being false, 1 being true. Think of it as your on-off switch at home. So when you turn it on, essentially it's on, it's 1. If you turn it off, it's going to be 0. That's actually how that symbol came about. Just something for you to know. Here are some examples of propositions. So today is Monday, it's raining. These are statements, these are propositions. Statements that are not proposition, it's again my opinion, C++ is the best language. Let's say, when is the homework due? These are questions and those don't become propositions. I want you to think about this. 2 plus 2 equal to 5. This is actually a proposition because it's a false statement. I'm not asking a question, I'm not implying anything along those lines. Every integer is divisible by 12. Same exact concept. I'm actually stating something. It could be true or false, but it's not my opinion, it's not something else. Microsoft is an excellent company. Now this is imperative. This is actually opinion based. It depends on who you're talking to. So that's not a proposition. You have logical connectives because in English language we don't necessarily just speak in true or false, right? We have different statements that tie in together. That's the same exact construct here. So logical connective, it's used to create a compound expression or compound proposition, and it ties in different types of propositions. So you have the first piece being negation. That's your symbol. That's the symbol we're actually going to be using throughout this. The way it's said is not A. Then you have a logical conjunction or a and, which is denoted by this guy, and it's basically the way you pronounce it is P and Q. Then you have or, which is denoted by this. It's P or Q. And this is an inclusive or. Now you also have an exclusive or, which is this guy, and we'll get into that a little bit more. And then you have an implication, which is again denoted by that. You also have biconditional statements, which can be denoted by these arrows. We'll talk about these different connectives and we talk about their values and the semantics of it using our truth table. So we will be constructing truth tables and working off of that. So like in your math, right, when you do math, you have a way of doing it. So BODMAS being one of them, where you define how you're going to go through different binary operators and what the ordering of those is. So that's exactly the same construct here. You actually have a preference in terms of parentheses. It's again, instead of even to avoid unnecessary parentheses, we actually hold the following precedences. So negation comes first, conjunction comes second, disconjunction comes next, or disjunction comes next, implication comes after that, and then you have your biconditional statement. So let's talk about negation first. So negation is this specific thing is called negation of P, which is the way you say it is called not P, right? So today is not Monday. This is not the case that today is Monday. These are exactly what those are. So if the truth table is P is 0 and 1, then not P flips over and becomes exactly the opposite. So your false statement becomes true, your true statement becomes false. Now your logical AND is a little different. Logical AND is true only if both the statements are true. So if there is anything other than that, it doesn't work, and it's called a conjunction. So essentially, if I give you two statements, one is P, one is Q, I need P and Q to be true. It doesn't work otherwise. So in this case scenario, for example, let's say we're going to do this one. So there we go. Example, it's raining and it's warm, so and so, Schrodinger's cat is dead, Schrodinger's cat is not dead. Let's say we want to fill that out on the truth table now. Both of these statements are false, or P and Q will be false. Oops. If you look at P and Q again here, one of them is not, so it's going to be false. Same thing here. And then you have true, because I need both those statements to be true for conjunction to be true. Now if you look at logical OR is a disjunction. So the way that works is essentially we're going to have a logical OR statement. So if you need one of the statements to be true, then both of them become true. So the way, or the conjunction becomes true, the disjunction becomes true. Again, it's a OR conjunction or a disjunction, one of the two things. So if you look at this specific thing, so if you look at this is, remember, this is going to be our conjunction, this is going to be our disjunction. So 0, 0, this is still going to be 0 because we're not doing anything else with it. 0, 1, because this is, so again in a conjunction or in an AND statement it becomes 0, but in an OR statement it actually becomes 1. Same thing here, same thing here. You just need one of those statements to be true, and that's how that works. Now exclusive OR is a little different from inclusive OR. So exclusive OR or XOR, it's true when exactly one of the propositions is true and the other one is false. So the circuit is either on or off, but not both. So in this case, for example, 0, 0, this is still going to be 0 because we still need one statement to be true. This is going to be true because I have one statement that's true, right? This is true here. In this case, I have this guy true. So I'm going to mark it out as true. But here, since it's both, it kind of breaks it down. So this doesn't work and this doesn't work. And so this is going to go back to being 0. So this is your exclusive OR. Essentially, that's how that works. Now, implication 1. So let's say that when we're talking about different types of implications. So let P and Q be different types of propositions. The implication Q is the proposition that is false when P is true and Q is false. So you need P to be true, Q to be false, and then it's true otherwise. So P is called the hypothesis, antecedent, premise, whatever. Q is called the conclusion or the consequence. So in this case scenario, you need that so in this case scenario, your truth table only becomes false when P is true, essentially when P is true and Q is false. So that's our only implication. Everything else, it's going to be true. So in this case scenario, since everything else is true, we can mark that out. This is going to be a false, and that's it. So that's essentially your implication 1. Now, the implication of P or hypothesis Q can also be read as if P then Q, or P implies Q, if P Q, P only if Q, so on and so forth. Multiple different statements. P is a sufficient condition for Q, so on. Again, multiple different ways of pronouncing it. So pick your choice and go with it. Implication 3. If you buy an air ticket in advance, it is cheaper. Not necessarily true. If X is an integer, X square is greater than or equal to 0, so on and so forth. Those are, again, that's your implication. If you look at the exercise for this one, so if if not 1 is a positive number, then 2 plus 2 equal to 5. Are the following implications true or false? So this is true because the premise is obviously false, but no matter what the conclusion is, the implication holds, right? We said that if, so long as So long as the implication is true, then it basically works out. If not 1 is a positive number, then 2 plus 2 equal to 4. Same thing as above. If sine of x equal to 0, then x is equal to 0. Now this one is false because again x can be a multiple of pi, and then again you can have a whole big implication where something will come true. So basically it cannot both be true. Then you have your biconditionals. Now biconditional is again if p, the way we're going to pronounce this is a little different. So the way we're going to do this is p if and only if q, right? This is only if and only if q. So this is true when p and q have the same truth values, otherwise it becomes false. Note that it is equivalent to p in conjunction with q and so on and so forth. So it says that if both of them have the same truth values, so both truth values are the same, these are your, essentially they're both the same, then you have 1, everything else becomes 0. Then you have biconditional too. So the biconditional p if and only if q can be equivalent, and this can be read again in different ways. So example is x is greater than 0 if and only if x square is positive. The alarm goes off if and only if a burglar breaks in, and such. So if you look at these if you look at the exercise for this, look at the conditionals. X square plus y square equal to 0 if and only if x equal to 0 and y equal to 0. Is this true or false? Well, it's true because x, if both the statements hold. Now 2 plus 2 equal to 4 if and only if root of 2 is less than 2. Is this true? It's true because again this makes sense. X square is greater than or equal to 0 if and only if x is greater than or equal to 0. Now this is a little tricky because you have two different implications. So x square, first you need to make sure that if x is greater than or equal to 0, then x square or x square greater than or equal to 0 holds. So basically you need to make sure both the statements hold completely. So if you look at it, it becomes false because I'm going to have to tie in two different statements and the different hypotheses where a conclusion can actually fail. Now you also have a converse, inverse and contrapositive statement or proposition. So consider this proposition: if p then q. Its converse is the proposition if q then p. Its inverse is the proposition not p if not p then not q. And contrapositive is the proposition if not q then, actually it's going to be not q if not p then. Remember, negation comes first. So constructing your truth table, actually we missed something, there we go. So if you look at this, truth tables are used to show and define the different relationships between the truth values of individual proposition and compound propositions based off of them. So now we can actually go in and check what we've done, and that should basically look more or less the same. Constructing truth table. So construct the truth table for the following compound proposition: p and q, this or not q, right? So the way we're going to construct that is, first we construct our p and q, which we did, then we do a not q, and now we tie it all in together, and that's where we go with that. Remember, or statement requires one of them to be true and such. And that's basically it. Thank you.